Hello friends, today we are going to discuss some of the practice questions for GATE exam thermodynamics 2021 forenoon session is our question paper. So we will start our first question. Superheated steam at 1500 kilopascal, and that is superheated steam, has a specific volume of 2.75 meter cube per kilomole and compressibility factor of Z 0.95. The temperature of the steam is. So here I have underlined superheated steam and the value of Z is 0.95. So if Z is equal to 1, we know it will behave as ideal gas. Since our Z is very close to 1, we can consider superheated steam as ideal gas and we will use PV is equal to ZRT. Here we should know what R we should use. Since it is given us in kilomole, so here we will use the value of R is 8.314, that is kilojoule per kilomole Kelvin. Since pressure is 1500 kilopascal into 2.75 is equal to 0.95 into R is 8.314 into T. So here will get the temperature in Kelvin, but the temperature they are asking us in degrees Celsius. So we have to reduce minus 273 from this equation. So the temperature that will come out will be 1500 divided by 2.75 divided by 0.95 divided by 8.314, that is 522.26 Kelvin. So minus 273 we will do to convert it into degrees Celsius, that is 249. So the correct answer is A. So we will move to next question. In the vicinity of the triple point, so that is triple point, the equation of the liquid vapor boundary in the PT phase diagram for the ammonia is this one, where P is the pressure in Pascal and T is the temperature in Kelvin. Similarly, solid boundary, vapor boundary is given by this equation. The temperature at the triple point is. In GATE, you should read the units very carefully. This is in Pascal and this is in Kelvin. So we have been asking Kelvin only. So we know the diagram. That is for so this is our solid phase, this is our liquid phase, and this is our vapor phase. This point is called triple point. What is the triple point property? That all the liquid, solid, liquid and vapor phase will meet at this point. So at the temperature of the triple point, the pressure will be same. So we can equate both the equations LNP and this equation. So we can write 24.38 minus 3063 divided by T is equal to 27.92 minus 3754 divided by T. we will multiply it with the t with the whole equation, and the result that we will get after solving this equation is T is equal to 195.197 Kelvin. So round off to one decimal place, we can write it as approximated to 195 Kelvin. This question is also very important, and अगर आप लोगों ने thermodynamics के previous year लगाए होंगे, then you can write this, solve this question in 5 seconds only. So we will solve this question. और जब भी आप क्वेश्चन सॉल्व कर रहे हो तो ये तो थर्मोडायनेमिक्स में बहुत सारे टाइम रिपीट होते हैं ऐसे पॉइंट्स, रिजिड, इंसुलेटेड टैंक, इवैक्यूएटेड. So rigid means volume is equal to constant. Insulation means Q is equal to 0. Evacuated means there is no nothing present at the initial stage. So a rigid insulator tank is initially evacuated. It is connected through a valve to a supply line that carries air at a constant pressure and temperature at this point. Now the valve is open and air is allowed to flow into the tank until the pressure inside the tank reaches to 250 kilopascal, at which point the valve is closed. Assuming the air behave as a perfect gas with constant properties Cp, Cv, R. So the final temperature of the air inside the tank is. So we have to solve this question. So we will do this thing. So we will make one tank that is like this, and it has a fixed volume, and it is connected to a valve and with a supply line. In this, air is flowing at a pressure 250 and temperature 400 kilopascal, 400 Kelvin. So there is only one inlet, there is no outlet at this point. So this question is basically related to our steady state, steady flow. So suppose at t equal to 0, this is the condition of the tank, and at time t is equal to t, when the gas reaches at a constant temperature, the final conditions in the tank are P is equal to 250 kilopascal. So here is we have to write the steady flow energy equation. So du by dt is equal to mi hi plus v1 square by 2 plus gz1 plus q minus me, that is all in mass flow rate at the exit, he plus v square by 2 plus gze minus w. Since the tank is rigid, w is equal to 0. Since there is no insulation, so q is equal to 0, z is equal to 0, there is no elevation difference, and mass at the exit is flowing is 0, there is no outlet. So the final equation that we will get, and there is no velocity. So I can write du by dt is equal to mi dot hi. And conservation of mass, we can write dm by dt. What will be the change in mass? mi dot me dot. That is rate of mass flow at the inlet and rate of mass flow at the exit. So dm by dt is the change in of mass in control volume. So suppose this is our control volume. So m2 minus m1 is equal to mi dot minus me dot. So we know at t is equal to 0, it is evacuated. So m1 is equal to 0, there is no mass present and there is no outlet. So m2 is equal to m1 dot. So I can write du by dt is equal to u2 minus u1 is equal to mi dot hi. So I can write it m2 u2 minus m1 u1 is equal to mi dot hi. Since we know m1 is equal to 0 at initial stage, so m2 u2 is equal to mi dot hi. So m2 is equal to mi, so we can write u2 is equal to hi dot. I can write cvT2 is equal to cp into ti. So the gas flowing at the inlet has temperature of 400 Kelvin. So T2 is equal to Cp upon Cv into Ti. So I will put up this value and the final temperature will be T2 is equal to gamma Ti. So 1.005 divided by 0.718 into 400. So the final temperature is 559.8 Kelvin. So round up to one decimal, we can write decimal to 559 or 560. Consider a steam power plant working on an ideal reheat Rankine cycle. So there is a reheat cycle and it is working on Rankine principle. The work input to the pump is 20 kilojoule per kg. The work output from the high pressure turbine is 750. The work output from the low pressure turbine is 1500 kilojoule per kg. The thermal efficiency of the cycle is 50%. The enthalpy of the saturated liquid and saturated vapor at the condenser pressure are this one. The quality of the steam at the exit of the lower pressure turbine is. So we will make its diagram. So we know for the steam it is a U-shaped dome curve. So this point is 1, this point is 2, this point is 3, 4, 5, 6, 7. So work done in the pump is 1 to 2, that is H2 minus H1. That is given as 20 kilojoule per kg. Everything is in SI unit, that is per kg. The thermal efficiency of the cycle is 0.5, that is W net upon Q supplied. So Q supplied is our from H3 to H4. And the enthalpy of the saturated liquid and vapor at condenser pressure are. So this is our condenser and its enthalpy is given at condenser pressure and temperature we have been given. So we will solve this question. So the work output from the high pressure turbine, that is H4 minus H5, that is 750, and the work output from the low pressure turbine is 1500. Basically, the work output from the low pressure turbine is more than high pressure turbine. We can see from this line also. This line is more vertical than H4 minus H5. So efficiency. So W net will be 0.5 is equal to W net work done by the turbine minus work done by the pump divided by QS. So 0.5 is equal to 2250 total work done by the turbine minus 20 divided by QS. So QS will come out as 4460, and efficiency is also equal to QR upon QS, that is 1 by 2. So QR will come as 2230. So I can write QR will be in this condenser, that is H7 minus H1 is equal to 2230. So H1 we have to find out. So enthalpy at this point is given as enthalpy of the saturated liquid is 200, and enthalpy at this point it has been given. So H7 we will know minus 200 is equal to 2230. So H7 is equal to 2430. So H7 I can write also as HF plus X into Hg minus Hf is equal to 2430. So Hf we have been given as 200 plus X into 2600 minus 200 is equal to 2430. So X will come out as 93%. So we will do reheat to improve the quality of the steam at the outlet of the turbine. So these things you also notice, because this type of things usually ask in IE duct, and this our exit duct, and it is supplying a continuous flow of air. Now, to maintain the quality of the indoor air, that is indoor air, the intake duct supplies a mixture of fresh air with a cold air stream, that is cold air, and this is fresh air. The two streams are mixed in an insulating mixing chamber located upstream of the intake duct. So this is our upstream that is coming to the intake duct. So here cold air and fresh air are mixed. So we have been given the condition of the cold air, that is 5 degrees Celsius and 105 kilopascal during the steady state operation. Fresh air enters a mixing chamber at 34 degrees Celsius and 105 kilopascal. So the pressure of the air remains constant. The mass flow rate of the fresh air is 1.6 times of the cold air of the stream. Air leaves the room through the exit duct at 24 degrees Celsius. So here temperature is being given as 24 degrees Celsius. Assuming the air behave as an ideal gas, so we have to calculate the rate of heat gain by the air from the room is how much kilowatt. So this is a steady state operation. So we can write here mass as m3, here write mass as m1, here write mass as m2. So P1 V1 is equal to m1 R T1. So if I will write P1 as 105 into 1.25 is equal to m1 into, it is given as 0.287 into 278. So m1 will come out as 1.645 kg per second. So m2 is 1.6 of m1. So that will come out as 2.632. Since it is a steady state operation, so m3 is equal to m1 plus m2. So that will come out as 4.27 kg per second. So now we have to calculate the temperature of the room at this point. So that air is coming at this point. So U1 plus U2 is equal to the temperature inside the room, that we can take it as UR, temperature, total energy inside the room, that will be sum of U1 plus U2. So we can write it as M1 CT1 plus M2 CT2 is equal to M3 CTR. So here temperature T1 is that is 278, and here temperature T2 is 273 plus 34, that is 307. So we can find out temperature TR at this point. So that will come out as 295.8 Kelvin. So the temperature of the air outside the room is 24 degrees Celsius, or we can write it as 22.85 degrees Celsius. So heat gained by the air is M3 Cp into temperature at T3 minus Tr. Why we have taken T3? Because we are assuming the process to be at constant pressure. Why we can use this formula U1 is equal to U2 plus U3? Because there is no heat loss at this point. It has been given insulated mixing chamber. So here the air is mixing and there is no heat loss at this point. So we can write total energy will be U1 plus U2 is equal to total energy inside the room. So N3 will be how much? 4.27 into 1.005, and this will be 24 minus 22.85. So it will come as 4.96. So it is in kilowatt, kilojoule actually. So answer will be our in kilowatt. So thank you guys.